This is the first-generation GHz femtosecond laser from Haomin Photonics. It features a compact design and operates on 12 volts DC power, and the laser uses fundamental mode locking to achieve ultra-low phase noise. The front panel with 3 ports, a power switch, an optical output, and an SMA interface. This laser is designed for a wide range of advanced applications. First, high-speed sampling. For example, in dual comb spectroscopy and dual comb ranging, the refresh rate can be significantly increased. Next, spectral canalization. GHz femtosecond lasers exhibit an evenly spaced comb structure in the spectrum, with comb spacing at the GHz level, making them highly suitable for broadband spectral canalization. Third, radar local oscillator. The laser features a high signal-to-noise ratio and can provide a local oscillator signal for radar systems, enabling low-noise electrical load generation at 100 GHz to 100 GHz, 300 GHz, and even for 100 GHz. Fourth, astronomical spectrographs. Astronomical spectrographs rely on fully stabilized GHz optical frequency combs. In addition, the laser can also be used for ranging systems that rely on GHz high repetition rate to improve measurement speed, as well as microwave photonics experimental links, or systems built based on GHz femtosecond lasers, and many other fields. Next, we will proceed with a live performance demonstration. This demonstration covers the laser's output spectrum, RF spectrum performance, and cold start time. We will first connect the instruments. We can see that the laser is currently in a standby state. After switching it on, the device completes the cold start and begins operation. On the RF spectrum analyzer, a very narrow comb line appears at the corresponding repetition frequency, indicating that the system has achieved stable locking. If the spectral line appears broader, it suggests that the system has not yet reached thermal equilibrium. Now, let's look at the optical spectrum analyzer. The current display shows the laser output spectrum with a smooth overall envelope. We then zoom in on the spectrum to measure the 3 dB bandwidth. Based on the definition of a 3 dB drop from the peak, the current bandwidth ranges from 1552.95 nanometers to 1569.3 nanometers, approximately 18 nanometers. After adjusting the vertical scale to 5 dB per division, the smooth spectral envelope becomes more clearly visible. Returning to the RF spectrum analyzer, the fundamental repetition rate of the laser is 985 MHz. During continuous operation, the line width remains stable with no significant variation. We then align the center frequency to the main peak and set the span to 10 MHz. While adjusting the resolution bandwidth RBU to 1 MHz. Under these conditions, the signal-to-noise ratio exceeds 70 dB. In addition, the sharp peak at the center indicates that the laser is operating in fundamental mode locking. If it were in harmonic mode locking or other regimes, a noticeable rise in the noise floor would typically be observed.